Welcome, this is Wireless Future. I'm Erik Larsson and I'm here as always with my colleague Emil Björnsson. Hello Emil, how are you?
I'm great, how are you?
I'm fine, thank you. So, what are we going to talk about today, Emil?
Research reproducibility, I think.
Research reproducibility, well that doesn't sound like a wireless thing, or is it?
No, it's not necessarily only something that's important in wireless research, but it's of course important there as well.
Indeed. I mean, reproducibility sounds like something that would be important in all sorts of research. Obviously, wireless in particular, right? But so where do we start this? What does reproducibility mean, really? And why is it important?
I think from a big perspective, it is really about that, well, we are observing the world and we try to make some conclusions from our observations about the world, and we have a hypothesis, is it this or that, and then we observe something and we try to draw conclusions based on that. And then we want to make sure that if we are repeating experiments or observe the world again, we will get the same conclusion. So we actually make a conclusion about the world in general and not just something that is just a coincidence from our experiment, for example.
Right. So I think this point with conclusion is important. I mean, if I pick up a die and roll it and it comes up 6, and then I read a paper about that stating that, look, I rolled the die and it came up 6. Would that be like a reproducible research in your view?
Now, the problem will then be, can someone else roll a die and come up with the same conclusion? Maybe you have a die with all the sides being 6, and in that case, yes, for that type of die and that type of experiment, everyone will get always the same conclusion. But it's also not very interesting if all the sides are 6.
Yeah, who knows? I mean, I rolled the die again, and this time I got 1, so
right.
Fair enough. But I would think, that there's got to be, in mathematical terms, some sort of notion of ergodicity here, such that we can actually estimate or say something about the world by performing time averages, right? Or the conclusion could be, well, I rolled the die 100 times, and 6 of the times approximately it comes up, now it came up 2, right? Okay, maybe back to the topic, reproducibility. Yeah. So there would have to be some sort of like statistical average or conclusion or a very well-defined thesis that research aims at reproducing, not just that, well, I rolled the die and it came up 6, but the specific property of the die that, well, the die is fair, or if I have a fair die, then it will come up 6 of the times, and so forth.
Yes.
So why is this an important thing to discuss to start with?
So since a lot of research is based on the fact that we are making experiments and we observe the world and then we try to draw conclusions about the world, we need to make sure that what we are doing is accurate, and that our conclusions are actually as general as we hope to be. And then it's both about sort of making observation the right way and then analyzing the observations in an accurate manner. And in particular in computational research, this term reproducible research have got a very specific type of definition, and that goes back, I guess, to 1990s. There is John Claerbout at Stanford who were looking particularly into how that would mean. So his approach was say, well, we have already made experiments, we have the data, but now we're going to analyze and compute things based on it. And we want to make sure that whatever we do in our analysis can be reproduced, in the sense that, he was saying, well, in addition to just reading a paper and see that there are some graphs there should be a button that you can click, and then the computer can go back to the original data and recompute everything so that you generate exactly the same graph.
Yeah, I first learned about this some 20 years ago. I think it's long ago. I think I was still a grad student, and I got back reviews for a paper that I have written, and one of the reviews stated something to the effect that you ought to look at John Claerbout's work and philosophy and making the research reproducible. And then I read up a little bit, and I think at the time at least he advocated like that you create make files, but nowadays nobody uses make files, but for those who are old enough to remember like how to do command line work in Unix or Linux, then a make file is like a script that recompiles from source all the code, and the idea was then to recompile all the code and all the like LaTeX files in the paper, so that you just start with source code and you end up with a paper including all the numerical graphs and numerical work. And I think, although the comment on the particular work I had submitted for publication seemed to be a little bit off the wall, I still took to heart this idea of reproducibility and found it to be generally a very good practice. Then there are maybe lots of reasons. I mean, there are lots of reasons why this is a good thing, and there are lots of reasons why many of the things we do maybe don't end up as strictly reproducible research, which I think we could maybe return to here a little bit.
Right. So I think it's also important to think about where did Claerbout start. So he was starting at a time where a lot of things in when you work with computers was very complicated, in the sense that if you have a Windows PC or a Mac, it was very hard to transfer documents between these things, and it might even be that Word, even Microsoft Word on a Mac and on a PC, you couldn't move things and expect they're going to look the same. And in that type of area where it was really hard to move data, then there was also the kind of thing, to what extent does your computations that you make depend on the computational environment? What operating system do you have? At what time of the day did you start it? And can you turn off the computer, turn it on again, and continue the computation and get the same thing? So that wasn't at all guaranteed, and it's not necessarily like that today either. So that is why having sort of ways of saving data or ways of saving your workflow in a reproducible manner is so important.
Yeah, I mean, in theory, it's all simple, right? I mean, a computer is a Turing machine, so just save the initial state, and then every time you run it, the output will be the same, of course, but there'll be like lots of things that might not end up with the documentation. For example, how you select random seeds and how the particular versions of your floating point libraries and all of that are implemented. So in a lot of experimental research, there is a distinction between reproducibility and replicability.
Right.
What is the difference here between the meaning of these two words?
Yes, so this is an important distinction to keep in mind here. So a person like Claerbout, he was working with the seismological recordings, for example. So you just have a small amount of data about earthquake, and they try to do different computations. So data was given, and they wanted to understand, okay, if we analyze this data and come to different graphs, we want to be able to go back to the same data and generate the same results again. So we can sort of be sure that we know exactly what computation we did. I mean, otherwise there is a risk you do some small changes in your computations, you generate the graph, and then you don't remember if you keep the same source code or someone changed something, and therefore you can't get the same graph again. But replicability is more about the idea that you should go back and not only use the same data, but generate new data, but do it in either following the methodology that someone had. So if you have a lab experiment saying that, well, you should do these kind of things in your lab, then you follow that notebook, but apart from that, you don't start from the same data, you do a new experiment. Or you can even push it to the point saying, well, if we would like to observe that the world behaves in a particular way, why should we even follow the same methodology? We should just gather new data, maybe in an entirely different way, but still eventually come to the same conclusion.
So you're saying reproducibility means that, well, given the same data set or same set of observations, then we would arrive at the same conclusions. Replicability is more like, well, stating the very same conjecture or hypothesis and put it up for test and collecting new independent data. If the experiment is replicable, then we would always end up with the same conclusion.
Right. Yes.
From the actual experiment, although the data sampled are different.
Yes.
Because, I mean, in science, there's also this replication crisis, right, where it is claimed that a lot of like papers and results published in experimental sciences, like in medicine, psychology, and so forth, just aren't replicable. So when other authors try to replicate the experiment and the conclusions, then even in the majority of cases, they aren't able to reproduce the findings, or replicate the findings rather. Is that anything we need to worry about? I mean, staying now with like the main theme of our podcast, which is wireless communications and connectivity, say research, is that anything that we need to worry about, the replicability or replication crisis, you think?
So I think there are important aspects to that to consider also in our area. So if you look at a typical paper that we are having in our field, it contains some mathematical developments perhaps, and in math, you typically, you write down some equations, you have a proof, you publish that proof, someone reads it and check that it's correct. And in that way, someone can also easily go back step by step and see if the logic holds in those mathematical parts. But so there, our research area, both in wireless communication and signal processing and related fields, are really good at checking things, and people can easily go back and replicate things if you skip over some steps to fill in those steps in your derivations. But when it comes to the simulation parts or even real measurements that are done in these papers, it's much harder to verify things are correct. I mean, as a reviewer, you can look at a graph and say, does this make sense or not? But whether the tiny details there are correct or not, well, you really have to go back and replicate the entire thing, unless the authors are giving their simulation code to you. So there is certainly the risk that there are errors. And there are different reasons for this replicability crisis. So I think one is, of course, that there could be just that someone drew conclusions that were incorrect. Often in experimental cases, you say you would like to be 95% certain, but 5% of the time you're wrong. And therefore 5% of publications should contain results that are wrong. But then typically it's more like 30, 40, 50% where they say it's hard to replicate. And there it can really go back to the thing that maybe the result is correct, but we cannot replicate it because it was poorly documented. And that is where the reproducibility research, where you sort of document everything because you can press a button and reproduce the result from the original data, that is solving that part of it. Because even if you in the paper forgot to write down a certain number, someone can always go down to your source code and check what did you actually make as an assumption there.
Mm-hmm. Yeah, and also, I mean, in general experimental science, there's this concept of p-hacking, where essentially the idea is that if you just sift through enough of data, then you're bound to find spurious correlations, right? Just think of it like if you generate randomly or semi-randomly a large number of time series, and then you look for pairwise similarity among them. Becomes a little bit like the birthday problem, that it's very unlikely that you won't find any pair of time series that look a little bit similar, although there's no causal relation between them. And the world is full of examples. I think one of the most fascinating that I saw was like, if you plot so as a function of time, you plot the number of times that Nicolas Cage produced a movie in a given, or appeared in a movie in a given year, versus the number of kids or people who drowned in a pool, then you see the covariation was almost perfect between them. But obviously it's very hard to think of any even remotely causal explanation for why they would be correlated. So p-hacking then refers to like sifting through huge amounts of data and looking for spurious correlations, and once correlation is found, imply that there might be a causal relation. And of course, observational science is all much of observational studies are based on looking for correlations, right? And now this is not necessarily only a bad thing, because by picking up correlations, then what we do is we do pick up signals that would prompt further investigation. Like, we see a covariation between quantities. Is there a causal relation in any way? And to test that, we would have to design a proper experiment to figure out, and so forth.
Yes. So I think this is a very good point. So it's a good way of picking up potential correlations and then analyze them further. But in addition to what you described, I mean, one of the dangers is that if you first do an experiment and then you look for a hypothesis that your experiment can confirm, and then if you have this 95% likelihood that you're looking for, that your hypothesis is correct, well, then you will be able to. If you test 10 of different hypotheses using the same experiment, some of them will happen to look like they are true just by coincidence. And so it's really this mixing of experiment and looking for the question to answer that is the important things. So I think in some experimental sciences, it's really like you first need to tell a committee, this is the hypothesis I'm having, and this is the experiment I'm going to run. And then you do it in that order, so that you cannot go back and sort of make up new hypotheses after you have collected your data.
Yeah, and there's also this confusion that seems also rather widespread between p-values of hypothesis tests and the air quotes probability that the hypothesis is actually true, right? I mean, just because a test shows statistical significance at the, let's say, 5% level, or as a p-value of 5%, does not mean that the probability of the hypothesis being correct is 95%. But maybe now we are drifting off the wireless topic a little bit too far, but it's anyways fun to go in that tangent a little bit. So back to reproducibility in our field. Are we, I mean, as not you and me, but the community in general, are we good at reproducibility?
Well, not in terms of the simulation parts, I would say. So the math part, we have been a lot about developing algorithms and proving theorems, and there I think we are very good. But for the simulations, we are not as good, and we are hopefully getting better because people are getting more and more knowing about this research reproducibility. I mean, I picked up about this topic from you actually at some time after you had understood or read about this from John Claerbout, and then I started to put out some code online for some of my papers, and at that time I didn't see so many other people doing it. I see more people doing it today. And I think there's a website, paperswithcode.com or something like that, where you also sort of, more people are doing it. But yes, there are quite some issues. And one issue is that we are not really in this clear distinction between replicability and reproducibility, because we often are setting up an experiment in the computer where we have a predefined set of assumptions, which might be our input data, but that we're going to do analysis on. But then we generate randomness in the computer. It's pseudo-randomness determined by a random seed. And then we start to introduce randomness within our computations that might not be reproducible on its own. And even if they are, then it might not be that if we run a Monte Carlo simulation where you want to use an average of a much randomness to approximate a true expectation, did we have enough samples to get an exact approximation there?
Yeah, so there are really at least two different things here, right? One is whether like the code is available such that we can be sure that we got all the implementational details correct. And in, say, classical communications theory research, that might not have been so hard, because all what we like tended to rely on were floating point libraries, maybe LAPACK for linear algebra and so forth, and well, there might be a small like machine dependence depending on how many bits, floating point, arithmetics that's being used and so forth. But in principle, you could take equations from a paper and you could hack them straight into your like favorite programming language and you would get the same result, right? This is more difficult now with especially with research that involves machine learning, with very sophisticated optimization libraries, with lots of parameters to tweak and tune, and that might not be documented in like the research papers, and where having access to the code and for reproducibility is a lot more important. And then I think the other aspect you mentioned here, which is also a highly important one, is how we generate and how we deal with randomness in the simulations, and particularly I would think in Monte Carlo simulation, right, where we estimate statistical averages by sample means, essentially, and then to make sure that we get exactly the same result if we rerun a simulation, we would have to make sure to initialize with the same random seed. So those are like two aspects here now. Ideally, of course, in a Monte Carlo simulation, you would run enough Monte Carlo trials such that it doesn't matter what seed that you initialized with, but there'll always be some small fluctuations, obviously, that remain.
Yes, exactly. And I think so that is very important. So if you save the random seed, then you can exactly reproduce the same graph. But it doesn't mean that the graph is an exact or very good approximation of what you're after, namely the average performance. And it could be average over random noise, random signals, random user locations, random this and that that you will have in your environment. And the more randomness we are introducing there, potentially the more you would need to consider different or a large amount of randomness to be sure that you actually get a small variations there.
Yeah, I mean, there are many pitfalls, right? I mean, or rather, when I look at like a Monte Carlo simulation result, I mean, the kind of canonical example, I guess, is to look at mean square error or bit error rate as a function of signal to noise ratio or something like that. And I always feel like a little better if the curve isn't entirely smooth, because at least it conveys the impression that the author has used independent realizations of the randomness for each point in the graph and so on, which are like an important practice to follow.
Yes, and here I think we also have this issue with that we come from a very theory-driven research area, so we haven't paid as much attention to the experimental computational parts of it, because in someone who's really building all the research on experimental, then you would compute confidence intervals for your Monte Carlo simulation and say, well, here is my curve, but the true curve is somewhere in between here with 95% probability or something like that. We seldom see that in our papers. It's not even guaranteed that people say how many Monte Carlo trials they were using to generate the curve, so it's even hard to figure that out. And
yeah, I think it's like implicit that if nothing is said, then the answer is enough, right?
Yes.
We ran enough until like this plot looked smooth, or I mean, maybe we can talk a little bit about concrete rules of thumb here for Monte Carlo simulation.
I think for bit error rates and the kind of error rates that is often simulated, there is some concrete rule of thumbs, isn't there?
Yeah, I think with error or like probability, estimates of probabilities in general, right? But if we think like communication theory, maybe bit error rate is the best example, or frame error rate or something similar for that matter. I mean, but a good rule of thumb is like if you plot bit error rate or frame error rate as a function of some independent parameter. Very often it's the signal to noise ratio on the channel, but it could be something else. Then a good habit is to count, I mean, at least 100 errors or bit errors per simulated point. I mean, if you just want to get a rough idea of how the performance behaves, then you could get away with counting maybe 5 or 10. But then if you are to write the paper or prepare a plot for any, like showing anybody else, then I'd say, well, count at least 100, and if you can afford it, like computationally, and you want nice plots to put in your papers, then maybe count 1,000 errors. And of course, this is easy to argue for by simple mathematics, because the observed number of bit errors will be binomially distributed with parameters equal to the true probability of error and the number of trials that you make, and the standard deviation of the binomial distribution is easy to figure out. So one can like analytically argue for why did you say 100 or why did you say 1,000, right? And of course, in the end, it comes down to what precision do we really, or what accuracy do we want to have in these numerical results. But if you just want like a number or a figure for a rule of thumb, that's what I would answer.
Yes, no, exactly. And that also means that one way of designing your experiment is that you figure out, okay, I can afford running 1 million bits. That is what I can transmit over my channel. And then that means that I can take not 10 to the power minus 6, but 10 to the power minus 4. That is the kind of random errors that you will get a good estimate of. And then below that, you can of course plot below that, but the slope of the curve will be very random. So that's why you should avoid doing that.
Look a little bit like zigzag like this, right? Which is, when you see that, it's an indication that there probably weren't enough statistics collected. And another rule of thumb that might be worth mentioning is goes for like any numerical experiment, more or less, that involves generation of synthetic random data, is to just rerun the experiment a couple of times, or even a handful of times, with different random seeds, and see how much the result differs from one run to the next. If you always get like the same kind of shape or the same output, like plot, then that will instill some confidence that fluctuations because of or inaccuracy because of insufficient randomness in the data, or insufficient number of Monte Carlo trials is probably negligible. But if the variation is large, then there's something going on. So.
Yeah, and I think that is hopefully what a lot of people in our field are already doing. They are running things until the point they get smooth curves. They are making this check that you were saying, and they are not computing confidence intervals. And maybe that is unnecessary, as long as you are confident in other ways that the curves are good.
Yes, I mean, hopefully this is what folks are doing, right, and what we teach our students to do. But you're right. I mean, rather than sitting down and actually penciling out like the confidence interval exactly, then this is more a way of just visually, by eye, inspecting or determining the confidence in the results. Yeah, so maybe back to like terminology a little bit. We discussed reproducibility and replicability. There's also this notion of open science. Do you want to elaborate a little bit what that means?
Yes, so this is sort of a larger concept that also include reproducibility, for example. But it's the idea that the entire research process should be open for everyone. So if you start from the end point, well, the publication should be openly available for everyone. Then you should be able to reproduce the computations. You should describe the method that you use to generate your data. You should, in a way so someone can replicate that one. The data should be available so you can reproduce it. And if there is software and all the different things, that should also come in there. And then in some cases, people even want to make the peer review system more open, either in the way that afterwards, if a paper is accepted, one can go back and see what was said in the peer review, or even that in some more extreme cases that you should just let papers be put out there openly, and then there should be a community effort to review new papers.
Yeah, I mean, it sounds good, right? It sounds almost like a utopia a little bit, that everything be open and you give away and so forth. But I think in practice there are obstacles here because you don't want to give away too much. And I mean, as an individual, you might not want to do it. As a researcher, you're sitting on some code that you spent hours, I mean, maybe years on writing, and you might be sitting on alternative like conjectures or thoughts that, well, if you give them away, they will like be your next paper, right? And as a corporation or organization that's funding research, you might want to maintain the edge by actually owning and benefiting from the results. And even as a country, I mean, you're funding research that, well, maybe could be like useful for humanity, but it's still the people of the country who takes the foots the bill, and it isn't maybe so obvious in the end where to like how much openness to require. But what I think we probably agree is that in general the philosophy of that research, scientific research, should be open, data should be open, reproducible, and so forth, is a good thing.
Yes. And so you're certainly right that there is some kind of trade-off there between, on the other hand, or on the one hand, letting people or countries have a competitive edge because they are the ones who do the main research, and it takes time for others to replicate or coming back to that, coming up to their frontline research. But on the other hand, well, if it's easy for people to replicate and start from the state of the art, maybe that will lead for the world as a big community to more swift progress. But the way I'm handling this myself is to say, well, I put out code often together with my journal publications, but not until after it has been accepted for publication, just because of the risk that we get rejected, someone else takes it and out-publishes us,
or data and publish the paper
exactly.
Before you. Yeah. Doesn't sound like a likely thing to happen.
And if you have an idea for future work, then you will probably initiate that work before the previous work have been fully published anyway, so then you keep some kind of competitive edge there as well, so it's some kind of trade-off here.
Yeah, ideally that's how it should happen. So speaking of like, and we talked about simulations and synthetic data, which are often random or pseudo-random to be more exact in numerical work in our field, and well, in many other fields for that matter. But it's also now more recently, I think, in, let's say, comms theory and wireless comms research, a trend to use data sets. And that is a practice which maybe is pioneered, I'm not sure, but is like, seems to be standard practice among machine learning research. Is this the right way to go? I mean, to have like terabytes of data that reside on some servers and that folks can download and try their algorithms on, rather than working with synthetic data they would generate from models or other means?
I think there are both good and bad parts of this. So I think the good thing is that everyone is comparing their algorithms on the same data, which means that we can be sure that if your algorithm is better than mine, it is truly that on this data at least. Because otherwise you can often see this kind of thing that, oh, you publish an algorithm, I publish a new algorithm, and I show I'm better than yours. The problem is that I only showed result in my own computational environment with my own assumption and not using your assumptions, which is a rather bad research practice. So having this data where everyone is competing against each other on the same data is showing clearly that you improve the state of the art over and over again. But the problem is this data set general enough so that it is important to beat each other on that data, or are we just over designing things for that particular scenario?
Yeah, I feel there are two problems at least here. One is that if there are lots of data sets available out there, doesn't that open up for a bit of like p-hacking, that you would design an algorithm, then you try it on all the data sets, and with some fluke it works very well on one of these data sets, maybe beats whatever is state of the art, but it's rather mediocre on all the rest, and then you like have enough to publish a paper. Look, I designed this algorithm and I tried it on data set this and that, and it worked great. And you don't disclose the fact that, well, on all the other data sets it wasn't really so great. And the other thing I think is that, as you already alluded to, that there might be a risk here that we over-design algorithms that are like adapted to the characteristics of particular data sets. So, I mean, in a way, it's a little bit like the same thing, right? That you pick a particular data set and then you optimize tightly your algorithm so it works well on that very data set. And the question is, what does this tell about generality of, like, if this is an algorithm, usually the way I want to sell it is to say that it's better than what's out there on the market. And
yes, and I think in areas like image processing, they have this huge database with a lot of images that you should classify, for example. And then it's often like, there might be 5 different big databases, and when you publish an algorithm, you show result for all of them, and you then showcase that you are particularly good at some and not on the other ones. So this is a practice that they're having there, whether it is the right approach or not. If these databases are general enough to cover everything, I don't really know. But in our field, I think we don't have this yet.
Right? Yeah, they have to be diverse enough, these data sets. Because, I mean, we one thing that we teach is never test on the training data, right? And in machine learning, it's like, well, make sure and there's enough generality so that when we train and we test on some data set, but reality will test it on yet other data that's unseen, and then we got to make sure that, well, we haven't trained and tested too hard on some specific data, but that what we developed really generalizes to reality. And of course that's difficult to prove, but I can see the utility of data sets, but I would maintain that for them to be really useful, they have to be extremely large and extremely diverse, like in wireless comms research. I'm not sure, but there might be data sets out there on like maybe wireless propagation and so forth, and then let's hope that these really cover all the conceivable scenarios that you could like end up with, so that algorithms you design and test and validate based on these data sets really are that great in reality in the end.
Yes, and if we think about the standardization of wireless technologies at 45G and so on, I think in an organization like 3GPP where you do the standardization, you define a certain number of simulation scenarios, macrocells, microcells, the line of sight probabilities and that kind of things. And then when you want to push new features into the standard, you need to demonstrate that you are getting a good improvement in performance on those scenarios, which is also one way of not necessarily creating a data set, but creating predefined simulation scenarios where you need to beat prior work. And I guess it's hard to push a new feature unless you actually are beating things there, people's previous algorithms. But whether that actually in reality, when you design the network or deploy the network, will actually showcase the same gains, that is less obvious that it will be like that.
Yeah. Anyway, so back to reproducibility, and we talked a lot about the advantages, right, and of advantages of making code available and so forth. But aren't there drawbacks? I think we did touch some. One is like the ownership of the data and the code. That if you own it and don't disclose it or share it away, then you'll have an edge because you're ahead of everyone else. Are there other drawbacks with like making code or simulation code available?
So one drawback, I think, is that it really invites people to reuse your code. So if there is something wrong in your code, that kind of errors will be propagating through other people's research. So instead of someone trying to
hopefully whatever student who looks at your code will be diligent enough not only to use it but also to really debug and double check and understand it, right?
And that is actually happening. So for a number of these repositories that I put out with code, I get emails from people saying, isn't there an error there, or how does this work? And a number of errors have been catched in that way, including in my Massive Miner book. There are several of the figures that turned out to be incorrect due to some errors that people were catching. So that is a great way of using the code, but it could also be that errors are not detected and they are propagating, and they wouldn't have been propagating if people were forced to replicate things from scratch instead.
That's a good point indeed.
And then I think it's also can encourage over-publishing more, because if you are only interested in trying to publish new papers, not in the top venues, for example, but only get a lot of it, you can take someone else's code, change a few parameters, generate something that looks different from previous work, but it is actually just a few days of work.
Yeah, especially for, simulation heavy work, there is of course the risk that somebody would like just change the scenario and then hopefully obtain the same general conclusions, but numerical results corresponding to different scenarios that look very different, so it could make it for their own paper. So I think to maybe start to wrap this conversation up, Emil, you might not be the pioneer in say with this idea of distributing or publishing your simulation code, but I think you're definitely a role model for it in the community. And I was wondering if you had any like practical advice to share. For example, where do you store the code? Where do you put it, like on your personal web page or on some other repository somewhere? And where do we publish like open papers and so forth?
Right. So in the signal processing community, I was at least asked a few years ago to write an article for a signal processing magazine called Reproducible Research, Best Practices and Potential Misuse. So we will link to that one in the description. And to answer your specific question, what I have been thinking about is you want to put your code at some place where it will be there, hopefully indefinitely, but at least for a very long time. And after a while, I've been converging to putting this out at GitHub, because you can do that freely, and it's nowadays owned by Microsoft, I suppose. So and a lot of people, software developers, are putting things there. So I believe it is a place that will be around for a very long time. I've also tried out some options of putting codes together with archive papers or trying to publish it along with publications. That is another option, but I think a lot of people are searching for code on GitHub, so that might be a good place to do it.
Yeah, so GitHub is the short answer.
Yes, but data sets you can't put really on GitHub. Yeah. So that is, the larger they are, the more you come into the point that someone needs to pay for the place where you're going to put this. And that also shows how publishing companies start to look into how can we monetize our reproducible research and open science in general. So you can pay some company to publish your code together with your paper. I think IEEE have some service like that, and you can pay them to take care of your data sets, and that might also be a way. Hopefully, as a publisher, their promise that this will be around forever, but it's also the question: are we supposed to pay more to make things more reproducible, or is open science more about
we're entering
paying less?
Another discussion here.
Yeah.
But I mean, so you're suggesting GitHub to be the place to go. Are there any competitors? I mean, say that somebody doesn't like Microsoft for whatever reason and they want to publish on GitHub, then could you publish it? Like, I would think even if you have your own personal like blog or your departments or universities. At least if you're in academia, I mean, you might have like a institutional repository or web page, and you also have like I think we have like a terabyte of storage on one of these cloud OneDrive. I think it's a Microsoft SharePoint backend where you can also put like data and you can link. Of course, it's kind of ugly because if you link there, it will be very long and ugly link that nobody can remember or type in. But there ought to be alternatives, I would think. Although maybe currently GitHub is one of the most user-friendly and seemingly stable places to store.
Yeah, I think the danger is really how do you make sure that what you put out there will be available for a very long time. So at least in Sweden we have the issue that a lot of these services, there is a procurement that is making resulting in that every 10 years or so maybe our web services are changing, and someone decides, oh no, you should not be allowed to have that much public data putting out somewhere. So I think you should really look for this kind of library services, either your own university library or there is then the archive where you put out papers, and it's really meant to be archived there, and you can put code there as well. I've tried it a few times, but the issue is that it's not so visible, but maybe they can improve in that in the future as well. And of course there is no guarantee that GitHub will be around forever, so this just I wanted to not put it at the university website, and particularly when I've been moving from university to university, it's also the issue that you realize, oh, I need to move it.
Yeah, sure. So, no, to be clear to listeners, I mean, this is not an advertisement for GitHub or its owner, but it does seem like a useful at current at least place to store this sort of data and simulations. I was also thinking like about other practical aspects. One thing that I learned the hard way is like when you write code, then there'll always be dependencies, and then you write something no matter what language you write. I mean, be it C++ or Python's very popular. Then you let it rest for some years, and then you pick it up and run it. Then invariably I get error messages that there is some package missing or somebody upgraded some package to a newer version, and then the API is changed so that the code doesn't compile. And is there like a best practice of what to do so that we can ensure that code written like years ago still runs on a modern machine?
Yeah, so I think you really need to specify what were all of the computer programs and libraries and things that your code depends on. What versions do you have of them? Because often if you know what library versions were used, you can go back and install those specific ones. Then it is annoying if you need to install something really old, and maybe eventually that will be very hard to do. But at least that is one important part of it.
Yeah, and it's not... I mean, it sounds easy to just write down which versions of the libraries that were used, but then in reality it is not always so simple, because these old libraries might not run on the modern OS, and then if you try to install an old OS on the new computer, then that OS doesn't support your modern hardware and so forth. So now we're entering like a bit of different tangent here, but it's not a super easy thing. I mean, to ensure that code we write will be possible to run like forever in the future.
No, and I think that was what's clear about, and others were in the beginning already thinking about. And I mean, in principle, you can create a virtual machine where you put all installed things into that one, and then you share that virtual machine so someone can start it. That might be the most secure way. That might be the thing.
I mean, again, fundamentally, it's a Turing machine, right? So it's all deterministic. That the result all follows by a deterministic set of like instructions that are executed in a deterministic Turing machine. Anything else here to add, like best practices around documentation? I feel like one thing is I think you've been really good at this, putting out like source code for your papers on GitHub, and think I released some occasional piece of source code long ago, and some folks do it. But I think, again, I mean, you're a role model here in the community. And one thing I feel like is if you ask students to do this, they'll be a little bit like hesitant because maybe they don't want to show their spaghetti code to their advisor or to not let alone to the rest of the world. And also, but that might be a good thing that to actually for you to be willing to show your code, you'd like it to be cleanly written, right? And you'd like to supply along with it some decent set of documentation. So I would think of this as rather an advantage that, well, if we force ourselves or our students for that matter to publish their source code, that will force us and them to walk through and debug the code one more time, maybe even refactor the whole thing, and think twice about even trivialities like variable names and so forth, clean it up, add documentation, which in itself is an important skill to acquire. Do you have any, I mean, you have a lot of first-hand experience in this process. Do you have any additional advice or insights that you want to add there, Emil?
No, I was basically going to say roughly what you were saying, that I was personally afraid of, I will expose myself to so much criticism by making it easy for people to reproduce my results, and they will figure out all the errors. But I think on the contrary, first I've been understanding, well, maybe that is not a bad thing. Maybe the important thing is that the research that is published is accurate, and if there are errors, people are finding them and can correct them. But then also, as you were saying, if you add this extra step, you think you're done with the paper, not time to submit it, let's do the following. Let's go through, copy your simulation files to a clean library, so you only keep the things that should be there and there is no inadvertent dependencies. Then you go through every file, you write comments and update them, you're making sure that parameter values that are written as assumptions are matching with the paper, and then you at the end rerun the simulation and see that it looks exactly the same as in your paper. Well, then you're sure that you have code that to your best ability is correct and it matches with the paper, so you can at least reproduce the result in the paper. Then I think this is enhancing the quality of your paper in the end.
Yeah, so now we're back at Clairboat's advice that we started off talking about, right? You start with a clean git checkout and run your make file, and it generates all the numerical, compiles some source, all the code, and generates all the numerical results and compiles the actual paper with everything in it.
Yeah, so it's really the right way of making sure that your result is accurate, and that is, I think, the very least we should do.
Are we overestimating how much, I mean, if we put simulation code out there, how much it is actually going to be used? I mean, because I feel like, you might look at code that folks have published, right? But in the end, if there's something you really want to understand, you probably want to implement it yourself, and you might get inspiration by looking at what others have done. It's a little bit like if you're teaching a class, then you might find from colleagues some PowerPoints or notes or even find on the internet. And for like myself, I would rarely use anything straight up that others have produced. I always prefer to like produce my own notes. And do you think that we are overestimating the actual utility of code that's being published, so that the real value here of the process rather is the process itself, like we just said? Cleaning the code, writing the documentation, ensuring that everything compiles from sources cleanly, and so on.
I think that is a very important part of it, that by taking this extra effort, you know that people will see your code, you will improve on it, and you will most likely find some small bugs when you're doing that and correct that and improve things. But then it's also like publications in general. Most papers are read by very few people, but a few ones are read by a lot of people, and in the same way a lot of code that is put out there, maybe very few will read them or no one will actually execute them. But in a few cases, it will be well read, and then it's worth the effort. And when people are approaching me and talking about my code with me, then it's often like young researchers who wants to understand how does professors write code, and how do we it's a way of kickstart your career by looking at other people's code and understand how to do certain things, and then eventually you need to do everything yourself, but it might be an efficient way of getting into a topic.
Getting started. Yeah, I fully agree with that. So great, Emil. Is there anything else that you think should be added to the topic?
No, I think we have covered a lot of these things. So I think the bottom line is really that we should always do our best to have a good research process, and that involves making sure to document your code and validate that you can reproduce your data. And then if someone tries to reproduce it and fails, we shouldn't view that as a bad thing, but rather a way of improving things eventually, and that we as a collective should do better research and confirm each other's conclusions.
Absolutely. Thanks a lot, Emil.
Thank you.
And to the audience, don't forget to like and subscribe to us on YouTube.
All right. Bye-bye. Thank you for listening.